So good morning all of you. Last class we were discussing on the X-ray X-ray resists, both positive and negative X-ray resist. We mentioned and we explained the basic principle of operation under exposure of the X-ray in the range of 5 to 10 angstrom wavelength, and their developing mechanism also we have discussed. Today again we will continue that X-ray lithography part, and here we are comparing the properties of positive and negative X-ray resists. The X-ray resists are sometimes known as electron resist also. In electron beam lithography, we will find in the next slides that we will use the same resists. Okay, X-rays are also basically some electron beam of some electrons are coming. So the reaction mechanism with this beam with the resist, as well as the in case of electron beam lithography or ion beam lithography with the same resist is similar. So now the resist used for positive X-ray lithography is PMMA and PBS, and negative is COP. And in this table shows the comparison of resolution of these three kinds of photoresist X-ray resists and also their sensitivity. In case of PMMA, resolution you can achieve less than 0.1 micron. In PBS, resolution is of the order of 0.5 micron, and COP it is 1 micron. So in positive resist, the resolution is better compared to the negative resist. So that is also true in case of optical lithography. Now the sensitivity is in case of positive PMMA is 600 to 1000 millijoule per centimeter square. That means that much amount of energy is required so that the resist is sensitive to that radiation. In case of PBS, it is 94. So you see here the energy requirement is small compared energy sensitivity here is 94 only. In case of COP, it is 175. So far as the energy requirement concerned, we will prefer PBS compared to the PMMA, because here 94 millijoule per centimeter square is only required. So again some other photo X-ray resist has come up. So those resists required in the range of 10 to 20 millijoule per centimeter square. So if the amount of energy required for complete reaction of the resist with the radiation is low, then the advantage is you can get higher throughput. And basic difference in negative and positive photoresist is threshold energy, as I mentioned in the response curve earlier, that threshold energy in case of positive resist is higher compared to the negative resist. So that's why although resolution is better in case of positive resist, but we found that throughput will be less in case of positive resist, because for getting that much amount of energy you have to expose it for a longer time. But if this energy is less and people are trying to find the resist composition, so that even in positive that threshold energy is low, so that we can have smaller exposure time and we can have higher throughput. So that is one of the directions one should think. And another is the X-ray wavelength. Normally PMMA is exposed with 8.34 lambda alpha K alpha aluminum K alpha X-ray. That means here aluminum is the target material in X-ray source. In PBS, target material used is palladium, and the radiation is coming from L alpha cell, and wavelength is 4.37 lambda. And COP also palladium L alpha cell radiation is coming, and there the wavelength is 4.37 angstrom. Now X-rays with wavelength between 1 to 50 angstrom, and that means photon energy between 10 to 0.25 keV, wavelength is small, means energy will be higher inversely. So they suffer negligible scattering as they go through resist material. And we have seen that the scattering effect is also proportional to wavelength lambda. In case of optical resist, we use ultraviolet light, and their wavelength is in the range of 300 to 400 nanometer. That means 2000 to 3000 angstrom. So compared to that, in X-ray we are using wavelength in the range of say 5 angstrom here to 10 angstrom only. So you can imagine how much the radiation wavelength has reduced. So accordingly, scattering effect also will be negligibly small. And the second advantage also will be from the diffraction. Diffraction phenomena is also diffraction is also proportional to wavelength. If wavelength is small, then diffraction is also minimum. So that way, the X-ray lithography, the advantage is scattering is less, diffraction is minimum because of the lower wavelength. And another point is the negative X-ray resist with sensitivities below 10 millijoule per centimeter square have been made by incorporating chlorine into the resist polymer. And just now I told you that people are trying to have a resist film which will have sensitivity in the range of 10 to 20 millijoule per centimeter square. Here is one example. So in 175 negative resist where sensitivity is 175 millijoule per centimeter square, there you can reduce it nearly 10 by incorporating some chlorine into the resist film. Similarly, in case of positive also, people are trying to reduce the sensitivity level in the range of 10 to 20 to 30 millijoule per centimeter square. So negative resist swell and contract during wet chemical development process. This is one of the disadvantages, as I mentioned earlier also. Because of the swelling, you cannot have more resolution in case of negative resist. Dry development by plasma processing avoids swelling problem and improves resolution. This is one of the solution. So this swelling and again contracting when it is drying, so that effect will not be seen if you go for wet etching phenomena, that means plasma etching. So there is no liquid, so there is no question of swelling. So that dry etching is a solution in case of negative resist if you want to get rid of the swelling problem. Another important aspect is negative X-ray resist with sensitivities below 10 millijoule per centimeter is obtained by chlorine incorporation into the resist polymer. The sensitivity of these resists is not adequate to achieve the goal of high resolution and high throughput. Sensitivity can be increased by increasing the X-ray absorption in the resist. Now here one point I would like to mention, that absorption coefficient. For example, people want after the lithography is over, the pattern will be straight wall pattern. So wherever resist will be there, so the resist masking, the layer will be straight wall. Okay. So that means you require uniform, because wherever the unmasked region, wherever it is exposing, there throughout the total thickness, the reaction will be uniform, so that during development, whole thing is coming out, whole thing is dissolved. So that means you need the uniform exposure throughout the entire bulk of the resist in the unmasked region. Where is not masked means where is transparent. The region which is transparent, so that total bulk resist should be reacted with uniform intensity of radiation. So in order to ensure that the absorption of the radiation by the resist should be minimum. If in the initial few layers, for example, the X-ray is absorbed drastically, then what will happen? The subsequent bottom layer, it will not get that much amount of energy. So that means you will not get straight wall after development. So that means the absorption of the radiation by the X-ray film should be as minimum as possible. One point, to get straight edge wall. At the same time, if X-ray is not absorbed, or whatever radiation you are using for in lithography process is not at all absorbed by the film, then what will happen? Reaction will not take place. It has to absorb, then reaction will take place. So these two are basically the conflicting requirements. So you have to come to a certain level where it will not absorb drastically. In that case, what will happen? The bottom layer will not be properly exposed and you will not get straight wall of the image. At the same time, if it doesn't absorb at all, then you will not have sensitivity, because if it absorbs, then it will react, isn't it? So that's why absorption coefficient may be increased by increasing lambda of the X-rays. Again, this absorption is dependent on what? Dependent on the X-ray wavelength. If wavelength is more, the absorption will be higher by the resist. And again, the absorption coefficient of the resist film is one parameter which is determining the straight edge vertical wall of the structure pattern. That means in the two way you can control. The adequate absorption you can ensure from the increasing the lambda of X-rays. And at the same time, you have to choose the photoresist film such that its absorption coefficient is not very high, so that the resist pattern is distorted. Clear? So these two can be handled or controlled in different ways. Next, I will discuss on X-ray mask. So X-ray mask obviously is different from the optical lithography mask, because the optical lithography mask you are using chrome plated or emulsion plated the glass plate. So there you can have the transparent and opaque regions, and if you expose with ultraviolet light, the ultraviolet light will pass to the transparent region and it will be obstructed at the opaque region. It will not allow to pass. But in case of X-ray radiation, what will happen? The mask which you are going to use in case of optical lithography, in that mask, both the transparent and opaque region, the X-ray will pass, both the regions. So that means it cannot be used. The normal lithography or optical lithography mask cannot be used in case of X-ray lithography. So you have to think separately for designing X-ray mask. The basic property should be the X-ray has to be absorbed completely. It will not allow to pass through the mask in a certain region where we don't want to expose by X-rays. And there should be certain region which is transparent to X-rays. X-ray can immediately pass through that, isn't it? So that means you have to look for a certain material which will absorb X-ray completely on the mask. I am not talking of the resist. On the mask plate should be such that some region the whole X-ray will be absorbed completely. In the some region, X-ray will pass through the mask so that it can expose the resist film underneath the mask. Clear? So for that, you have to have some transparent layer and some layer which completely absorb X-rays. The absorbing layer for X-rays, we use gold film. Gold film can absorb X-rays perfectly in the range of lower wavelength, say 5 to 10 or 20 angstrom region. Soft X-rays, I am not talking about the hard X-rays. Here the X-ray source, we are thinking of soft X-ray source. And transparent region, which is known as the membrane region, and for that we can choose polyimide, silicon carbide, silicon nitride, alumina, Al2A3, or sandwich of oxide, nitride, oxide material. So these are membrane materials. Membrane means through which X-ray easily pass. Okay. Now in this diagram, you can see this is a X-ray mask diagram, and there you can see there are several layers. One is the protective coating, and next one is the gold, the pattern gold, and below that is the polyimide, is of the order of 6 micron, and below that is boron nitride, and below that some silicon and pyrex glass beam. That is the periphery. This is a cross-sectional view of the mask. Okay, that means when you are making the mask, you are designing the gold film, 0.6 micron gold film here, that you are going to design. So depending on your mask data, the gold film is patterned on the polyimide film. For membrane material, we are using here polyimide. It's a polymer material. Okay. In optical lithography, you are using the glass. On that, some emulsion coated film was there, and the emulsion coated film was depending on the mask data, this is removed or it was kept there. So black and opaque and transparent regions you are getting. So here the gold film, somewhere it will be there and somewhere without the gold film. So that is depending on the mask data you are creating, and that is on polyimide film. And now below polyimide, a boron nitride layer is again used, is a thick layer. So that is to give the rigidity or some support of the film, because you see this is 0.6 micron and polyimide film is again 6 micron, then total is 6.6 micron. So 6.6 micron is very thin. So that you cannot handle in the mask aligner machine. 6.6 micron, you can imagine how thin it is. So you have to have some support material, and that support material is such that X-ray can easily pass, X-ray will not absorb in that material. So boron nitride is one such material which gives a good rigidity of the total film. Film means here the polyimide film and the gold film support, and it allow to pass X-rays completely. So that means in this region where this polyimide membrane is there, through that it can completely pass through that. Okay, and in the boron nitride, that means layer is the gold film, polyimide, and the boron nitride, and throughout the periphery a thick rim of pyrex and silicon is used so that it will not put any scratch on the boron nitride film. So some periphery ring, silicon and pyrex combination is used, and on the top a protective coating layer is also put in order to prevent damage of the mask, means damage of the gold film pattern. So this is the complete structure of X-ray mask. Now let us summarize the function of each layer used in X-ray mask. Thus an X-ray mask consists of a patterned metal X-ray absorber on a thin membrane that transmits X-rays. Thickness of these absorbing material are determined by 3 parameters. What absorbing material we are using here? The gold. And how much thickness of gold you are going to use, it depends on 3 parameters, namely X-ray wavelength of interest, because absorption is dependent on the wavelength, as I mentioned in the earlier slide also. X-ray wavelength of interest. Second point is the absorption coefficient of the material, because the X-rays should be completely absorbed by the gold film. So obviously how much thickness gold film we put, that will be decided by the absorption coefficient of gold film and the wavelength of the X-rays. And the third one, contrast required by the resist to an image. So these are the 3 parameters which will decide the thickness requirement of the absorbing film, which we are using here gold. Next, membranes are highly transparent to X-rays so that exposure times are minimized, dimensionally stable, rugged enough to be handled frequently. So depending on these 3 requirements, exposure time should be as minimum as possible, dimensionally stable, and ruggedness. Keeping in mind these 3 aspects, we have to choose the membrane material, and as well as thickness of the membrane material. And here I showed we have used polyimide material of thickness 6 micron. And ruggedness is, again, for ruggedness we are going to use any support material, which is basically the substrate, we can say, which is boron nitride, the third one. So third one is used for ruggedness, as well as it also transmit X-rays completely. Okay. Now I will discuss a X-ray lithography aligner system, the schematic of an X-ray lithography aligner system. So here you can see the diagram. One should be the X-ray source. The X-ray source is here, and how the X-rays is emitted, the basic principle is you have to, there should be a target material, and you have to create some electron beam, and those electron beams are accelerated so that those beams will hit the target material, and from the target X-ray will be emitted. So that is the basic principle. And the target material may be aluminum, maybe palladium, maybe other things also. And depending on which target material you are using, the radiation, X radiation comes from different cells of the target materials, and wavelength also differs. For normal applications, we use palladium as a target material, and that target is kept here, palladium target. You see, it's shown here, palladium target. And electron gun is here, you see a ring. This ring is the electron gun. It's shown in the diagram, you see, this is a ring. This ring is the electron gun, it's shown here. So now, from the electron gun, electrons are emitted, and it has to be directed towards the target material, and that is done by electric field. Electrons are charged particles, you apply a positive potential to a high value, so that it will be accelerated towards that, and it will hit. At the same time, electrons beams will be focused onto the target, palladium target, and the X-rays will be emitted from the target, and you will get the diverging beam of the X-rays. From the target, the X-rays are emitted, shown here, X-rays of wavelength 4.37 angstrom. So those are emitted, and it's divergence beam. And now your job will be to focus the X-rays so that you can have a collimated beam of X-rays. Lot of divergence means intensity will not be uniform. You have to a collimated uniform intensity beam, and that is possible by using some focusing arrangement, which is electrostatic or electromagnetic, because those are all X-rays are charged particles. And also here you can focus it by using some by putting some X-ray absorption material in the diverging in the path of the diverging beam. For example, here you see these are diverging, and at the center of that diverging X-ray beam, you have used here a small hole surrounded by a material which can absorb. That may be the lead material. Lead can absorb X-rays, you know. And X-ray, you put a lead sheet here, and on the lead sheet you put a hole, and through that hole the X-rays will emit, and rest of the portion X-ray will absorb. And similarly, here use the beryllium window. That is in another material instead of lead. You can use lead, might be contaminated the whole resist and other system. So you can use the beryllium window. So that can absorb the rest of the, and you can get the central region only allowed to pass, and so that you may be collimated beam, because X-ray very difficult to focus using the electromagnetic lens, means electric or magnetic energy, which is normally done in case of electron beam or ion beam lithography. Now, those X-rays will pass through a chamber, and which this chamber is filled with helium gas. The purpose is to prevent air from absorbing X-rays. Whatever X-rays passes through that from the source into this chamber, so they should not be absorbed by other materials. And if it passes through air, air has got different constituent gases and other materials which may absorb X-rays little bit. So this chamber is filled with helium gas which will not absorb X-rays, and the X-rays are emitted from the chamber with uniform intensity through these windows. Okay? And here is an XY stage, and this microscope arrangement is for optical alignment. So there you are not going to use X-rays, but you use ordinary optical rays for alignment, because for alignment you have to see. You have to see the mask layer, you have to see the resist layer, and you can align the previous mask level onto the next mask level, so that proper XY movement arrangement should be there and alignment is satisfied. So when here is the wafer and this is the mask, and this is a stage where you can put XY stage, where you can put the wafer which is held properly by using some vacuum suction, and mask is put, then you align everything. When alignment is satisfactory, then push the whole thing into the here, this portion, and then it is exposed. In some of the machine, what is done, the XY stage is fixed, the whole optical house, it moves from this portion to this portion. That means alignment is done separately, then the mask and wafer combination is pushed back below the radiation, so that it will expose for a certain time, and that is done by using some automatic shutter arrangement. And the X-ray chamber product where you are producing X-rays, that chamber has to be evacuated. That's why some vacuum flange is shown here. Vacuum pump is connected here, and another system water cooled target, because if the palladium target is hit frequently by the high energy electron beam, heat will be generated, and that heat has to be dissipated. So you arrange for some water cooling through the target, so that the target will not be heated extremely, will not be hot, and you can get proper X radiations from the source. So this is the total schematic arrangement of the X-ray lithography aligner. The complete diagram, complete thing is not shown here. It is not so simple, highly complicated. Okay. Now, X-ray lithography. In conclusion, we can say the X-ray lithography offers best condition for achieving submicron resolution with high wafer throughput. Full wafers can be exposed in about 1 minute using existing resist and X-ray sources with resolution better than 0.5 micron. Okay. So these two conclusions we can make from the X-ray lithography. Now we will discuss some of the advanced lithography techniques. One is deep ultraviolet lithography. I told some of the advantages of the X-ray, but the disadvantage and the problems of X-rays I didn't mention. I should mention also that one. And the main disadvantage is the complication. You see, starting from the source and guiding the X-rays, focusing the X-rays, also is much more difficult compared to the optical lithography system. And in X-ray lithography, normally the lithography is done projection lithography. It is not contact printing and proximity. That's why you have seen in the mask at the periphery a guard ring is used, which is silicon and glass, and that is very thin, so that the mask plate and the wafer some gap is maintained. That is about 25 micron gap is maintained there. And another problem in X-ray resist, that is not optical resist. And the third problem is the mask. Making X-ray mask is rather difficult compared to making optical mask, optical lithography mask. These are some of the problems. but main advantage is there because of the lower wavelength of the X-rays. Scattering effect is less, diffraction effect is less, resolution is very high compared to optical, proximity effect is also small, and over and above, any dust particle which is a opaque in case of optical lithography, in X-ray it is not. So dust particle will not act as a mask in case of X-rays, and it will not damage the pattern, lithography pattern. These are the advantages. Other than the X-rays, some other lithography systems are there which are deep ultraviolet lithography. Then we will come to electron beam lithography, then ion beam lithography, and others. So deep UV lithography is again optical lithography. Only difference here is the optical radiation we use in deep UV is 200 to 300 nanometer. Normal lithography uses 300 to 400 nanometer. Here wavelength is less. Wavelength less means you will get advantage in case of reducing the geometrical optical effects. Optical effects mainly diffraction, scattering, etc. And resolution also improved in case of lower wavelength radiation. But the thing is that here you can use optical resist, ordinary optical resist. Here you can use same mask which you are using optical lithography mask. So that means by reducing the wavelength of the ultraviolet rays, we can improve the resolution and lithography features without complication which is required in case of X-ray lithography system, without lot of problem which we face in X-ray lithography system. So here for commercial deep UV source, xenon mercury lamp is used, which can produce the radiation of 200 to 300 nanometer wavelength. To achieve straight wall resist straight wall resist image profiles, the resist must absorb a small percentage of incident radiation. Small percentage. This small percentage is about people have simulated it is about 10%. If it absorbs about 10% of the radiation, then it's okay. If it is a more than 10%, say 30 or 40%, then you cannot expect the straight wall resist image profile. Too small absorption increases exposure time and throughput is less. So here again the same point which I discussed earlier, that one is the absorption coefficient and another is the wavelength. Wavelength of the radiation is such that here wavelength is reduced, so automatically the absorption by the resist will be small. You can get straight wall resist image. And the next point is told, the small absorption again increases the exposure time, which will reduce the throughput. This absorption is decided by the resist field. You can make resist field so that it increases, it absorbs quite to a large extent, so that the exposure time should be less and throughput should be high. Usually electron beam resist is used for deep UV lithography. So you see, if you use electron beam, then those problem is taken care. The exposure time small, that means absorption is more, which is not in optical lithography resist, optical resist. Although you can use, in case of deep ultraviolet light, you can use normal optical resist, but there the problem is this exposure time longer and throughput less. To reduce the exposure time and throughput high, to make throughput high, you can use X-ray resist, but mask will be the same as optical lithography mask. Use of deep UV and quartz mask plate instead of glass increases resolution to nearly 0.5 micron. Okay. These are few points, you can say important points, which tells us why deep ultraviolet lithography is a better one compared to the normal UV lithography. Now coming to electron beam lithography. Electron beam lithography, we use electron beam for irradiation of the X-ray, for irradiation of the photoresist film. So here for electron beam lithography, we use not optical lithography resist, we use the electron resist, PMMA, PBS and COP. Electron beam lithography is designed for optimum performance in research and development. Focused electron beam of diameter 0.01 to 0.5 micron is used. It is used in production of photomask, not normal lithography. You see, if you use an electron beam of diameter nearly 0.1 to 0.5 micron, then that electron beam has to be scanned onto the mask to expose. That means here exposing the whole wafer is the time consuming. So you cannot expect higher throughput. So commercially you cannot use it. That's why it's mentioned this particular lithography is used for making mask, and it is in research and development area. Commercially you cannot use it because the focused electron beam is scanned over the mask to expose the resist. Okay. It is used in direct writing on silicon wafer. So DSW, direct step write, that I mentioned earlier, there is another printing technique. So that is used for making the mask. Less throughput, 1 mask per hour. So you can imagine, if 1 mask per hour is the production rate, you cannot use this lithography in commercial purpose. These are the main features of electron beam lithography. So another is alignment accuracy, which is plus minus 0.2 micron. So the electron beam lithography is ideally suited for making high resolution mask. Okay. So now the schematic diagram of electron beam machine is shown here. So here you can see the electron gun, which is the source of the electron beam. Then you are using beam blanking. That means beam blanking means this can stop the electron beam to pass through this path and comes or radiate. The radiation is incident on the mask. Okay, this is beam blanking. Next is deflection coils or lenses. So that is obviously electrostatic lens. You can apply a field so that it will be confined. That is the magnetic lens or electrostatic lens you can use. Then in the vacuum chamber, the electron beams are guided to incident on the electron resist film, and this is the mask and wafer holder. So the electron resist is here, is the substrate, and this is the table which can move in x, y and theta direction. A mechanical drive is connected and which is computer controlled. XY mask data is fed into the computer, and depending on the mask data, the beam blanking will open or close so that X-rays can pass. Focused beam of electron beam will pass through this path and it will incident on the resist coated wafer through the mask. And table position monitor, that is also controlled by the computer depending on the XY mask data. So this mask data controls the position of this XY positioner where these mask and resist coated wafers are kept. At the same time, it controls the beam blanking arrangement, and a mechanical drive is there that is also controlled by the computer. Depending on the mask data, all the parameters, that means XY stage, beam blanking, that means it is basically the shutter, the mechanical drive, all are controlled by the computer, and depending on the the movements are all depends on the mask data. So you can expose and develop, and you can get electron beam mask. Okay. So next, I'll spend on ion beam lithography. So regarding the advanced lithography systems, we discussed X-ray lithography, we discussed electron beam lithography and deep ultraviolet lithography. Now ion beam lithography. Ions have heavy mass than electrons. You see, ion beam lithography and X-ray and electron beam lithography, the schematic diagram of the lithography systems are almost same. So here, instead of electron beam, we use ion beams, and ions have heavy mass compared to the electrons. And because of the heavy mass of ions, proximity effect is less in this particular lithography. And the proximity effect is due to backscattering phenomena. And I think you remember this the proximity effect phenomena, because backscattered radiation can expose the film also, which will deteriorate the film, the resist pattern. So that backscattering will be low in this particular case, and because of the low backscattering, the proximity effect will be negligible in ion beam lithography. And here scattering effect is low because of the heavy mass of the ions compared to electrons, and ion beam lithography also offers high resolution. So these are all advanced lithography techniques. At the end of lithography chapter, I would like to introduce another parameter, another thing, which is inorganic resist. So far, the resist we discussed either in optical lithography or electron beam lithography or X-ray lithography, those resist materials are organic in nature. All are organic materials. But now, some R&D has been done to find inorganic resist. And one such resist is germanium selenide coated glass. Germanium selenide glass solvable in alkaline solution, but when doped with silver, it is not soluble. If on the germanium selenide silver is coated, now we expose, in light induced silver migration on germanium selenide glass, you coat silver, then you put the mask, then depending on the mask, the silver coated germanium selenide mask will be exposed some region, and some region, opaque region, it will not be exposed. Where the light is incident, there the silver will migrate into the germanium selenide. That is known as photo doping. Here the doping is with the help of photons. The silver will dope into the germanium selenide material if you expose with light. but the region where opaque, so there light cannot pass, and silver will not dope germanium selenide, and that is not dissolvable. You see, the germanium selenide glass when doped with silver, that is dissolved in alkaline solution. That means wherever the light reacts with light is incident on silver, that silver is doped into the germanium selenide, and that germanium selenide will be dissolved in alkaline solution, otherwise not. So this particular property will help you to have a lithography system using negative inorganic resistance. What property we are using here? We are using photo doping of silver in germanium selenide. Clear? So this is on inorganic resist, and if it is perfected, its resolution is good, then we can use it in lithography also. So with this, I just conclude the chapter lithography. So in the lithography chapter, what we discussed, basically the techniques of lithography. Then we discussed the optical lithography in detail. We have studied the both positive and negative resist, its working principle and its developing action, and its merits and demerits. After that, we discussed on the lithography techniques, that is mask aligner machine. And the mask aligner machine, basically three printing techniques: the proximity printing, projection printing, and contact printing. All these three techniques we discussed, and then we mentioned the advantages and disadvantages of the different techniques, and also another technique which is known as direct step right, DSW, that also we mentioned. And then we came on the problems of optical lithography. That means its effect, geometrical effects, which is scattering and diffraction, interference, standing waves, proximity effects, all we discussed. They will distort, because these are all optical effects. These optical effects are going to distort your image on the resist film, because basically what you are doing, the image on the mask is transferred on the resist film. So that if image is distorted, you will not get the exact replica of the mask onto the silicon wafer or on photoresist. Okay. So how to remove those problems, that also we discussed. Then we discussed on the tolerances. Okay. How much tolerance you have to give, how much uncertainty is there in tolerance, which is defined by nesting tolerance, and its expression also we derived. After that, we came various advanced lithography techniques, mainly X-ray lithography, ion beam lithography, electron beam lithography, and then deep ultraviolet lithography, etc. And electron resist also we discussed, and those electron resists are useful both X-ray resist lithography, X-ray lithography, ion beam or electron beam lithography. Okay. And then little bit of inorganic resist advancement in lithography, because earlier all resists are organic, and inorganic resist also we came to know, and its basic principle we just discussed. Okay. With this, I just finish this particular chapter, photolithography.